The week before I came here, I was at Utah skiing, and they have powder snow up there. It's real powdery, and when you fall, you don't hurt yourself as bad. I went skiing in Colorado one time, and I hit that ice, and I think I broke every bone in my body. It felt like I did anyway. So I like that old powder snow. It's pretty good. And it is dry. You can't believe how you pick it up and your hands don't even get wet. But then I came up here, and it's supposed to be springtime. Today is the first day of spring, isn't it? Mm-hmm. Somebody messed up on that, didn't they? All right. Let's look at Module 14. This is groundwater. How many of y'all actually work with groundwater? You work with groundwater. Wonderful. How many wells do you take care of or manage?
7.
7 wells.
Anywhere from 350 GPM to 1800.
1800? About how deep are your wells up here?
From 50 to 110 feet.
15 to 110?
No, 50 to 110.
50 to 100. Oh, wonderful. And that's the well itself, or is that where the bowls are set?
Bowls are set on 110 foot. We start at 80 and they ended at 100. 20 foot bowls.
10-4. So y'all have some fairly shallow water. In Texas, our water can run anywhere from, if you go through a confined layer, about 100 feet all the way down to 3,000. In West Texas, you have to drill anywhere from 3,000 to 4,000 feet to get to the water. Around Bryan College Station, where our office is, it's around 1,100 feet to 2,000. But down where I live along the coast, we're anywhere from about 500 to about 1,000 feet.
You're talking a lot of bowl assemblies to get that water up from that deep.
Well, that's just where our water is, unfortunately. We have a lot of table water, but the water in the upper stratus are, how do you say, got a lot of iron, sulfur.
And kind of drills straight well that deep. That's a drill.
Oh, yes. And all that good stuff. But let's look at the Module 14. Let's look at the terminal objective real quick. Let me flip over there. And got to get back into the mode here. Terminal objective. Upon the successful completion of this module, again, you and I as an operator, and folks, Bessie and I are both operators. We're no different than y'all. We've had a lot of good mentors throughout our career, so we're going to share what we've learned from other operators also. We'll be able to describe how groundwater is made usable. So the whole purpose of this is to make groundwater safe for human consumption, really. Make it, palatable, aesthetically pleasing, and all that. Then the enabling objectives, those things that support or help explain our terminal objective. Discuss the relationship of aquifers to types of wells. And of course, aquifers can vary in thickness, permeability, and actually the materials that make up that aquifer. They can be extremely different. Okay, discuss common methods of groundwater treatment. And so basically, those are the 2 areas that we're going to focus on. And didn't put that up there. Yeah, discuss the relationship of aquifers as types of wells and discuss the common methods of groundwater treatment. All right. Now, sources of groundwater, we have precipitation, and it either rains, snows, sleets, or hails, and a lot of that water runs off into our streams or in our lakes and goes on out to the bays and stuff like that. But some of that water percolates down through the soil, and some of it collects in what we call unconfined areas. This is down below the soil. We're going to have an impermeable layer, and some of the water is going to be entrapped in that area. It's not confined above. But in that impermeable layer is cracks and fissures and stuff like that, and so some of the water is going to continue to pass on through that impermeable layer and get down into our aquifers. And some states or some areas of the country, the only water they have is unconfined water. In Texas, we have one area like that. It's called Wichita Falls, and it's called the Seymour Formation, and that's the only water they have. But like where I live, we have what we call the Evangeline Formation, and it's fairly shallow. It's between 500 to 1,000 feet down, and it's confined between two impermeable layers, and they're under pressure because the water stacks up. That's what causes the pressure. Does that make sense? Okay. And but if you look at this drawing, it really doesn't tell you a whole lot. The type of material or the media depicts on how readily available that water can be withdrawn. The more the colloidal the particle, the more difficult it is to bring out of the well. The larger the grain, the easier it is to dewater, but it doesn't hold as much water. And so we have to look at all of those things, okay? And of course, then the cycle starts over again, you know, evaporation and stuff like this, and transpiration. Transpiration is that moisture that comes off of plants and trees and stuff like that, goes back up into the atmosphere. And then, of course, we have normal evaporation off of our streams and lakes and plus the bays and all those other things. And some of the ones we don't even think about is perspiration. You and I consume water. We drink water to do a lot of things, lubricate the joints and flush out things and to keep us percolating. But we even sweat, you know, and so we even put moisture back into the air to a certain extent. All right. Now, if you look at the major aquifers throughout the country, and I cannot tell you, you know, over here where Rhode Island is, it'd be very difficult to, I think that's Rhode Island right there. And I don't know exactly which aquifer this is. Do y'all know the name of the aquifer that you're drawing from?
I'm out of the main brook aquifer. It's small. It's a local aquifer. Not part of a big regional.
Right. And you can look on there and see that. It's a very small area. And but all this area is like out in West Texas, and some of the areas, this is where the Seymour Formation is right here in Texas. That's where one of our instructors lives up there at Wichita Falls. And that is all unconfined water right there, okay? And but down here where I live about right there, right in that area. And Miss Bessie lives right over here in Houston. And most of this right here is called the Evangeline. It's made up of the Wilcox, the Yawa, and a couple of other different layers of aquifers in there. And it's quite large. You can see how large that area is. And it's quite thick. But the problem is it's got a lot of iron in it, a lot of sulfur and other stuff. So it has its disadvantages too. If you look right here where this yellow, this darker yellow is, that's really not an aquifer at all. That's where the fault line runs. That fault line starts up here in Maine and comes all the way down through here, all the way to Mexico City. That's the largest fault line in the world. And that fault line there has changed the direction of the Mississippi and the whole Ohio River 3 times in the history of it. The largest earthquakes is always across there. And so really it's caverns. There's no media in it at all. And so when it rains, water percolates down and gets into those caverns, which really act like almost like a storage tank. Now, when you get over here into Florida, Florida's got some uniqueness. It really has no groundwater. All of its water is spring water. And the manatees really love that water. It's really, really high quality water. Florida is blessed with a lot of high quality water. But they have to protect that because that's really the only water source they have, unless they go to desalinization or something like that. And then when you get out to like West Texas, this land is virtually worthless. You'd have to drill all the way to China to try to hit any water probably. And so they rely on the Rio Grande or the Rio Bravo del Norte, which comes all the way up and goes up here into Colorado. And the Elephant Dam sits about right there. And Elephant Dam is at 10% of its capacity right now, so that's extremely low. And right now they have not had a whole lot of snow. But as you can see, the center part of New Mexico virtually has no water at all. So they're relying primarily on surface water. The same thing in California, the Joaquin Valley and Napa Valley. That's virtually the only water they have. And that's because of the runoff from the mountain snows and stuff. And so they're very dependent on the snows there to percolate down into the soil. And when you start talking about the Rocky Mountains start and they come down through New Mexico and end up in Texas. And then they start again over here in Mexico. Some of the tallest mountains in the northern hemisphere are in Mexico. Mexico City sits on a 17,000 foot mountain. It's pretty big. But the water runs from the northeast to the southeast through the rivers. And really the reason they call them the Rocky Mountains, if you took the outer layer off of them, it's nothing but gravel. Big boulders, big star rock, bull rock, and stuff like that. And so there's a lot of water that is entrapped in the Rocky Mountains. And that water runs toward the Gulf of Mexico. And so Texas benefits from a lot of the rainfall and snowfall that they get up here in Utah and Colorado and New Mexico. And so that's one of our big benefits. But if you look at the United States as a whole, there is not that many major aquifers. They rely more on minor aquifers than anything, the small aquifers and things like this. So it's a pretty good little map and gives you an idea of where the water is. And that's where the people want to live. Because if there's no water, there's no reason for staying there, okay? And I'm going to put a little bit of this on the bottom. This was what we would call a table well, okay? And the reason is it's confined below, but there's no confining material above it. But then you come down to what we call an aquifer. An aquifer has a confining layer above and a confining layer below, okay? And the pressure that is exerted is what forces the water. When you punch a hole through this impermeable layer, the water pressure, the weight of the water is going to force it up to the tube. And if it was high enough pressure, it could actually come out of the top of the tube as an artificial artesian well, if it should come out through the top. But these two different wells are the main types of construction that you'll see throughout the country. Like I said, around Wichita Falls, this is the only water they have. Down where I live, this is primarily what we have. And the reason is because we have real shallow soil where we live. We don't have enough soil to hold much water. We only have the reason we raise rice, the soil is so shallow, and plus rice has to be flooded. If I had to flood a very big area, it would cost so much money to keep that land saturated to where the rice would be sitting in water. But because our impermeable layer is so close to the surface, we don't have to pump a whole lot of water to keep it full. Does that make sense to you? So sometimes these table wells can be quite large. Up around Wichita Falls, table wells can be as much as 150 to 200 feet deep. So there's a lot of soil up in that area that can hold water, okay? If that makes sense. And of course we have springs. When you talk about a pond or a lake, even though it has an impermeable, maybe a clay layer below it, the water is going to seep down into the ground, okay? And eventually it passes through this impermeable layer. Now, like I was telling you, and I talk about Texas because that's where I'm from, out at Fort Davis, it's in the middle of the desert, and plus the Balmorhea Springs are in the middle of the desert. But what happens, this aquifer right here, comes the soil dips way down and comes so close to the top of the aquifer that water bubbles out. And that's what Florida has a lot of. Florida has a lot of springs because the aquifer is so close to the surface that the land comes down to that impermeable layer, and that way we have natural flowing springs. In Texas over there by San Marcos and New Braunfels, that's the main flow of the Guadalupe River is spring water. In fact, it's 300,000 cubic feet per second when it's fully loaded. That's a lot of water coming in. And so we have those types of things. Okay, and then the water table wells, we talked about this one. And then the artesian is the type that's in between two impermeable materials, and recharge. And if you look on page, let's see, on, well, they really don't give a whole lot on that part, but if you look on page 14.7, there's just one little paragraph in there, but it's a pretty good paragraph. Aquifers are recharged by percolation from rain, snow, and seepage from rivers and lakes. Problems are occurring in many parts of the country where groundwater is withdrawn at a faster rate than is being replaced. This overpumping, called mining, results in declining water levels and, in some areas, subsidence, which is the sinking of the land. This is quite prevalent in a lot of areas throughout the country now. Around Dallas, Houston, because they're taking so much water out of the ground that they have had a tremendous subsidence problem. Parts of Houston have settled as much as 16 feet in the last 20, 25 years. One of my favorite places to go when I was young was down, they used to be a seafood restaurant, and it was called the San Jacinto Inn. It is now underwater. That's how much subsidence has taken place because they were taking it out. And what happens when you have media and you draw the water out of it, you're dewatering that media. And eventually the weight of the soil will make that media collapse, where all the little voids and angular spaces were in between the particles is now being compacted. And thusly we have subsidence. Not long ago, was that in Florida, where they had a sinkhole where that man was literally swallowed up? And, that would be a nightmare in itself, wouldn't it? Wake up and you're being swallowed up by the earth. They said they never did find him. And the sinkhole, when they sent that camera down there, was over 150 feet deep. And they don't know where he went. And so that could be a major concern right there, sleeping on top of a sinkhole. But that's pretty good, okay? And then, of course, recharge from, seepage from lakes and rivers. Overpumping can be a problem throughout the country. And the wells, construction. And before I get there, though, I want to talk a little bit about the different nomenclatures. It's in the book, but I think it's good to see a picture, and I like to use black, okay? We talked about surface water or well water. Let's say this is the surface, and let's say down here I have an impermeable layer of clay, okay? Impermeable layer. And so we get percolation, and we're going to have water fall into this soil, and it sinks down till it gets to this impermeable layer, okay? Now, this right here, if you ever take a groundwater examination, is known as the zone of saturation, okay? Saturation. All right. The area that does not have any water is known as the zone of aeration, okay? That means it's been dewatered, okay? Now, when this water is not in motion, dynamic, test question, a lot of times on examples, they'll say when water is not moving, it's static, okay, not moving. But when water is in motion, it's called dynamic, okay, it's moving. And of course, the dynamics of water is dependent on a lot of things, you know, friction, how much water, the percolation, permeability, and the size of that media, okay? Now, when I come along and I poke a hole, let me get my eraser right here, and I poke a hole down through this layer, and I put a pipe in here, and I come down here, and this area is screened, okay? This is where my slots are. And a lot of times you can have a submersible well, you can have various times, you can use various types of pumps, airlift pumps. I think the most common now is submersible with the motor and the pump both being in the well, okay? Now, whenever I draw water out of the well, I'm going to be dewatering some of this. So I'm going to have what is known as the cone of depression, okay? Cone of depression, okay? And literally, there is no water in this zone. It has been totally removed. Okay, so this is known as the static level. And a little bit ago, if I was to dewater this zone, this would be what? Pumping level? There you go. Okay, pumping level. Okay. And then the difference between the two would be what? Yeah, drawdown. And so we have the drawdown. All right. Now, if normally the water is traveling in a certain direction and I have a water well, okay, a water well is such. Well, the cone of depression is going to be sort of oblong. It's going, because water is coming back in to fill this void, then it's going to take longer for the water to get to this point, okay? And this is known as the circle of influence, okay? The circle of influence, okay? All right. And here's the problem. If I was to drill another well too close to this well, I'm going to have mutual interference, okay? I'm going to have, if both of these wells were running at the same time, I'm going to be drawing from the same water source. So it's very important that my wells be spaced such that I do not have what? Mutual interference. Does that make sense? Okay. Now, if you were looking at it like this, we're going to go in this direction. So if this was down, if my water was flowing in this direction, we have from the center line of the well to the outskirts of the cone of depression is known as the radius of influence. Okay, influence. All right, the radius of influence. The water is moving across this plane, and thusly the cone is going to be obscured. Okay, does that make sense? Because water is moving toward the low point, or the pressure, where the pressure is least. Make sense? Okay. Now, on an aquifer well, there's only a few minor differences. Okay. In a table well, you completely dewater that area. Now, here's the thing. What affects the static level is, like this gentleman was saying, how much rain you get. How much am I taking out? How long is a drought? That water, or that static level, is dependent on those things, like drought. How much water, how much rainfall I'm getting. Okay, does that make sense? Okay, now, let's look at an area where we have a mountainous area, and here's the slope of the ground, and out here is the ocean, or the bays, and I'm going to have what is known as an outcrop area. So I'm going to have an outcrop area, And this outcrop area, there's going to be an impermeable layer, like such. Okay, this is an impermeable layer. And then I'm going to have another impermeable layer. Okay, this is another impermeable layer. And in here is my water. This is my aquifer. It's full of coarse sand, gravel, whatever. Okay, now let's say that I come over here and I'm going to punch a hole in the ground. So I come over here and I punch a hole in the ground through that first impermeable layer, and I put a casing, okay? And then I'm going to cement this in real good through that first impermeable layer. Then I'm going to put a screen down in here, and the water's going to rise up to a certain level in this tube, in this outer casing. Now, this is known as the static level, when the water's not flowing. Now, when I turn the well on, it's going to drop to a certain level. Let's say this is my pumping level. Okay? Now, I've got my bowls down in here. Here's my tube. I got my bowls on here, and I'm drawing water out. This would be the drawdown. But I'm going to get an artificial cone of depression. It's going to look like this up here, but really it's down here in the aquifer, okay? We see this as our cone. But is the cone dewatered? Test question. In an aquifer well, is it dewatered? No. The reason is the water is stacked up in here. And all of this pressure is forcing that water to the low pressure zone. So I got high pressure, low pressure. That's what's causing it to rise in the tube. But when I turn the pump on, I even reduce that pressure more. Thusly, I'm going to be dewatering this zone, but not completely, because the water under head pressure is going to be rushing back in faster than you can dewater it. Now, how do I know that the water is still in the aquifer? If I turn the pump on and I dewater it and I break suction, what happened? I've dewatered it. So the size of the pump is dependent on how much water this aquifer is willing to give up. All right? So basically, this area right here is known as the zone of pressure reduction. Zone of pressure reduction. Let's say there was 100 psi down there. Now it might only be 60 psi. Make sense? Mm-hmm.
It's because it's moving.
It's moving, yes, sir.
It's like running a hydrant. You got static and residual pressure.
Yes, sir, very much so. Does that make sense? Okay. This is the difference between a table well and an aquifer well. Okay? And so it's very dependent on those elements, that stuff. Now, when we talked about the media inside of the well, some of the terminologies and the size of the media is very important. You know, if I have large media, and let's say they're golf ball size media in here, and I've got these particles, and they're nice and spheroid, meaning circular and everything. I've got this much open angular space, this porosity right there. It holds a lot of water. But when I turn my well on, do I have enough water available that will be able to supply my system? Okay? Now, if I go down to media that's the size of, let's say, marbles, okay? I get marble size media. I have the ability to hold more water because I have more angular space. Look at it like this. If I was to put these marbles inside of this golf ball, I have created more angular space. So I hold more water, but I also have what? More static friction. Water has the ability to conduct electricity. There's minerals in it, metal salts and stuff like this. And thusly, it has the ability to sheen to the surface of the media. Now, if I get down to media that is so small, it holds a lot of water, but because of its magnetic attraction to the media, it will not give up its water. Okay, does that make sense? So we have to choose a media that has the ability to hold a lot of water, but also has the ability to give up its water. Okay? Now, believe it or not, only about 5% of the media that are in these aquifers have the ability to give up reasonable amounts of water. Only 5% out of all the medias that we've ever drilled in. Now, can we get it out of the others? Yes, but at a tremendous amount of cost. You want to add something to that, Miss? Okay. And so it's really important that we, a good driller is going to be able to assist us with that program. And let me tell you something. When it comes to cotton and rice, I can tell you anything about it. But when we drilled a brand new well out there for the rice farm, this old boy's over there with his fingers as that stuff is coming out of the ground. Oh, that's good, that's good. And it feels like snot to me. I have no idea what he's feeling. But this is good. And I said, how do you know that's good? Oh, it's just, can't you feel it? And it felt like slime to me. And I said, no, I can't feel anything. But those guys that are good drillers with all their years of experience can tell you if they're in good aquifers. How many of y'all have ever drilled a well? Anybody ever drilled a well and actually feel that stuff coming out of there?
I've only done when we've had wells drilled.
Mm-hmm.
But I've seen them drilled.
Yeah, did you feel the material?
Yeah, I felt. It's funny because the whole when you're doing when you mention that, then they'll run a little pump test to establish a specific capacity for that. No, where they should they go deep or should they go shallow?
Right.
They look for where they have the best capacity.
Right. And they're good at it. You get a good knowledgeable driller and they can tell you all that stuff. Yeah.
They make a nice little log for you after it shows what's in the ground, but they take samples the whole time they bore on.
Yes, sir.
So that way they track.
Right.
They track what's in the ground.
Right. And it's really amazing to me how good those folks can do. And if you look over here on page 14-6, you can actually see where two wells are drilled too close together, and you can see how they're mutually influencing each other's production. Now, some towns do this on purpose, and let me tell you why. When you are talking about drilling, media is drawn up to the screen, and sometimes the media can clog part of that screen. So what they do, they alternate the wells. This well comes on, runs. When it cuts off, then the second well comes on after that. And it pulls the media away from the screen of the second well. It helps to keep the screens clean. And they purposely do that. That's expensive, but in some areas where the material is very colloidal, small particles, they do it on purpose. But neither well runs at the same time. They alternate the wells. And very, very important. Okay. Now let's go back to wells in our construction. And this really starts over here on page 14-7. And again, we have to look at the media. And going back to your records, if you talk to area drillers, they know where the best water is. You take like in this area here, there is no telling how many wells are out there. But there's history on those wells. And so all of that history is what? Knowledge. Now, if you talk to somebody who recently drilled a well, they might be able to tell you a lot about how much production they get, what size pumps they had to use, there's a lot of historical data out there that can help us choose a site, okay? And it's really helpful. Then they normally will not drill the actual well, they will drill a test well first. And that way they can test the quality of the water, they can look at the different various medias, and if there is a zone in there where they might have iron problems or hydrogen sulfide problems or sulfur, they can put a blank in there. Instead of putting a screen, they will put a blank and then go below it. They'll have screen above it, below it, but that way they're not drawing in the latter or the worst type of water that might cause quality problems for your customers. And so that's normally what they do. A test well is very beneficial. And so we go from there. And when we talk about construction types, we have dug with shovel and buckets. You know, back in the old days, at our farm is fairly old. And it's been in the family for 200 plus years. And there's an old dug well out there and it still has water in it. I would never drink it, but how do you say, it was dug by shovels, and literally they went down there and lined it with bricks and stuff like that. And it's fun to look at, but I wouldn't drink the water. Okay, and then bored with augers. A lot of table wells are dug with augers. And the problem with this though, is when you drill with an auger, you have problems with the soil falling into the well, okay? It's normally done in more stable areas where it's more cracks than really media. And so they use the auger type system. A few years ago, when those miners got trapped and they went down through there with an auger, and boy, you talk about some tough ground. That was some tough ground. Driven with a dry point. Do y'all have to de-water? Like if y'all are laying new water lines or sewer lines, do you have to ever put in well points or sand points to de-water the soil? Have y'all ever done that?
I've seen that done.
Yeah. A lot of times if you live near the coast, you have a lot of water in the soil. And before you can ever lay your water mains or your sewer mains, you have to put in driven well points. They put a pump on there and they de-water that area so that they can dig their trenches to lay their pipe. And it's done a lot along the coastlines. Down in Galveston, they do that a lot. I'm sure they do it along the beaches over here, wherever they have homes being built and they need to de-water that soil. So they're driven and then they hook it up to a pump and can de-water that area, okay? And then we have drilled wells is the most common. Like in the old oil well days, you have your drill bit. The drill bit, you might see it like this. It'd be like 3 heads on it. They're at an angle and they've got grinder teeth on it like such. And they got grinder teeth, so you're looking down at it and you've got these different angles. You got one coming off over here, and then you got one coming down over here that's got the teeth on it and stuff like that. I'm not a good artiste, but how do you say? Like this, and they got the grinder teeth mounted on here and stuff like that, and they got the teeth, and then the pipe is hollow. The pipe is hollow. And this is where the drilling mud comes in. The drilling mud does 2 things. One, as it's drilling the hole, it's lubricating the drill bit. But it also is forcing the aggregate out of the well. Okay? So your mud is coming down through the center of the stem. It forces the aggregate up, out, and into a catch basin. The aggregate is heavier than the mud. It settles out, and then you can take the mud off of the top of the holding tank and reuse it for drilling. It's like a circulation thing, okay? Does that make sense? Okay. And these are made of various materials, okay? Now, the most important thing is the collars. The collars is the weight, okay? So when a driller is drilling, he needs enough weight that he can grind away the rock. But if he puts too much weight, it could cause the well to what? Bend, because it's just too much weight and it's bouncing around in there. The driller has to know exactly how many collars to put on the system. If he puts too much, it's too much, and if he doesn't put enough, it just sits there and spins. So they have to be very knowledgeable to that, okay? And then they have what is known as the Kelly, and that's at the top of the well, and it's the part that swivels while the machine is turning, the turntable is turning, grinding away the rock, and then you have your drill stems, and you can go down. Normally they're anywhere from 20 to 40 feet to even 60, 80 feet in length. And like I said, they drill the materials out, pump it out, and try to reuse the mud as much as possible, because mud is not cheap. The other purpose of the mud is to keep the sidewalls of the bore from caving in. They act like a cement, okay? They act like a temporary cement wall to keep the media from falling back down while you're drilling. And if you're drilling in gravel, very difficult to keep the gravel from caving in. Does that make sense? All right, I say that a lot, I don't know why, but we go from there. Okay. Now, the other thing too is once we get through and we put the casing in and all that, let's talk about that real quick, because this chapter is fairly good, but okay. Now, once the driller drills from the ground through this impermeable layer, okay? Here's my impermeable layer. And we drill down through here, and he's got his casing. So he's got his casing coming down in here, down through the first impermeable layer. And of course, here's our angular spot right here, and comes up to the surface. Now, he is going to pump concrete or a sealer. He's going to permanently mount this casing between the bore hole and the outer casing. So he's going to use cement stabilized material and pump it in between the void, fill this void all the way from the top to the bottom on both sides. Okay? This is what Halliburton does. Halliburton does this. And so does several other companies. They cement the well in. Okay. Now, here's the thing. If this is done incorrectly, if I have a flood and water gets down between the casing and the outer wall, it could get down here where? Into our aquifers. Okay? So it's very important that when we drill a well, that it's properly cemented. Okay? Now, also, when you drill a well, if you have a, let me redraw this. If I have rolling hills like this, I wouldn't want to drill a well down in this valley or this low area, because if it rains, it could what? Flood. I want to choose areas that I get substantial drainage. So I want to pick an area that's higher so that the water runs away from the well rather than toward that well. Does that make sense? All right. And so we're going to cement that well in. Now, one of the things that you have to remember, when the water rises up in this casing, when we turn the pump on, this is going to drop. But when the well turns off, this water is going to flood back into the outer casing, and it could cause shock. So what we have to do is we have to put a breather on here and it's a gooseneck turned down. It needs to be large enough that it will cushion the fall of the water back into the outer casing. So we're going to have a vent, and it has to be a 16 mesh screen that covers that vent to keep the bugs and insects. Mud daubers, in our area, mud daubers are our worst enemy. Do y'all have mud daubers up here? These are those things, they make their houses out of mud.
Wasps.
The wasps, okay.
Same thing, they make them out of, it's like cement.
Yeah, it's like cement. And they can plug up that thing. So we put a 16 mesh screen over there. So when the water turns off, air can be drawn in to cushion the fall of that water. And that creates from damaging your seal and also prevents damaging the outer casing. Does that make reasonable understanding there? Okay. So we have to have a vent. All right. I'm sorry.
That's okay. We had one well where the vent was too big, and when the pump came on, it was shut to hell. It was like a hammer.
Oh, is that right?
Yes, because there's a check valve. There's a check valve there too, because it's got to be able to vent only one way.
Right.
So you actually got two vents, one for when the pump starts, one for when it shuts off.
Right.
So we actually had to put a valve on it and throttle it back to slow
it down.
Slow the release of the air when it started, when the pump started, because you're venting the casing.
Mm-hmm. Right.
And that slowed the water down, because I mean, the pipe would literally jump on the cradle.
I'll be darned. 10-4. Yeah, so that's good to know. Yeah, 10-4. And of course, the outer casing must extend 18 inches above the finished floor or the ground, whichever is higher. Okay? 18 inches. So that's very important. All right? Now, when it comes on down and we go down to the next impermeable layer, we're going to drill on down and we're going to have a hollowed out area and we're going to insert the screen, and basically we're going to put like a gravel pack. Okay? Now, let's just say this is the size of my particle inside of the aquifer. I can go in here with a gravel pack that's twice the diameter of the media itself. So I can go in something there that's slightly larger. Okay? And so I'm going to fill this in with a gravel pack that is slightly larger than the media. That way when I put my screen in, my screen will be the same size as my media. But the gravel pack will be slightly larger. Thusly, I can increase the size of the slot and have a better withdrawal rate without this sand being able to get into the slot. Okay? Make sense? Okay. So we can do that, and that helps. Now, when we do this media, remember this media might be contaminated. So we have to disinfect it with 50 milligram per liter dosage of chlorine before we put it into the well itself. So we have to disinfect this gravel pack beforehand. Make sense? Okay. And stuff like that. Now, if you look over here on page 14-8, we're going to talk about the upper part or the inner casing. Okay, we'll do that on the board too because I like showing that picture. I think it works better. Okay. And Miss Bessie, if you want to add anything as we go, do. Okay, let's say here's my finished ground and here's my casing coming up out of the ground. Well, let me do it a little bit lower so I have a little bit more room to draw. Okay, so here's my casing coming out of the ground. And a minute ago, one of your questions, the ceiling block. What is it made out of? It's made out of concrete, okay? And, you know, around the well, we're using pressurized cement right here. This is pressurized cement to make sure the area is filled in, the angular space is filled in real good. Remember, this must extend at least 18 inches above the ground, and it must be vented, okay? And we'll draw it out here like that. And we got a vent with 16 mesh, okay? But with the ceiling block is to give you an extended area of protection. Now, it must have a 1/4 inch per foot slope, okay? So you can never be any higher than 1 inch from the top of the casing. But the outer edge must extend a minimum of 3 feet in all directions from the outer casing. Now, let's just say I just install a conventional ceiling block. Well, the outside edge minimum is 6 inches. And so if I was to slope this at 1/4, that's another 3/4 inch, right? So the minimum thickness up against here would be 6 and what, 3/4 inch? But I can come all the way up to this point, and that's if I wish. It's not necessary, but a lot of people do. Okay? And make sure if you're looking down on the well, there's going to be a 3-foot extension all the way around the well, and it's slightly sloped at 1/4 inch per foot. That's to keep the rainwater from, and this allows you to put your pumping head on and your seal so that you can keep water from getting into the system.
So that ceiling block, say you've got a 12-inch casing, so now you're talking a 7-foot diameter ceiling block, correct?
Mm-hmm.
Okay.
Yes, sir. Yeah, absolutely true. He was saying if this is 12 inches, then we come out at 3 feet, this would be what? 3.5 and 3.5, so it'd be 7 foot from the center line. Yeah, absolutely true. Yes, sir. Okay. Now, let's go to the inner casing. All right. So we'll redraw this. And here's my outer casing again. And here's my surface. And here's my ceiling block. And now we're going to insert our head. And up here is the, I'm going to, hypothetically, here's the head and here's my inner casing. And it goes down into the well. And down here's my bowls. Might have 4-stage. And here's my static level, hypothetically. And this would be my pumping level, hypothetically. But let's talk about what we need on the discharge side of the well, okay? Let's say over here it's going into a ground storage tank, okay? Now, the first thing that I need to do is, what do I need? Number one, you have to meter your water. But before I do that, I want a safety device built in there. So I'm going to put a check valve, okay? Oh, well, let me make a little bit more room. All right, let me take this out first. I got to put an air relief valve again, a vacuum breaker. And so I'm going to put a vacuum breaker in here. And again, I got a goose down. And here's a ball valve. And what happens? When the well is on and water's coming out, it's going to push this ball up against the seal, a seat. And when the well turns off, again, this is 16 mesh corrosion resistant material. When the well turns off, this ball drops out of the way and allows air to be drawn in. So the water that is inside of the inner casing is cushioned, okay? Now, just past that, I'm going to put a check valve. This is to keep the water from running back out of the ground storage tank back into the well, okay? Then I'm going to have a meter to register my raw water. Normally it's a turbine type meter, okay? And then I'm going to have an isolation valve. The isolation valve is if I have to work on any of this material, I can isolate it. Then I'm going to have a test cock. Okay? Test cock is to collect my raw water samples in the event that I need to run those tests. And this gentleman's had to do that, so he knows about that. And then let's say that I'm going to have chlorine, and I'm going to show where my chlorine comes in, my disinfectant. All right? And this is all necessary on the discharge side of the well. Make sense? All right. Those are the few things you must have. And again, this right here is an important device in that it prevents shock to the inner casing. All right. And here's, of course, here's my motor up here, and I'm not a very good artiste. And this shaft goes back down here to the pumps in here. Okay, pumps in here. All right, we got our pumps. Does all that make sense so far? Okay. Now, when you drill a well, all right, we have to know what the static level is and the pumping level. Okay, so let's just say I have a well up here. Let me draw it in. Here's my ground right here, and I've got a well going down here. And here's my impermeable layer, and then I have another impermeable layer, and I've got my screen down here, and then I've got my motor, and I've got my pipe coming down here, and on the end of this pipe, let's say I've got 4 bowls, and here's my static level, and right here's my pumping level. And of course, we know the drawdown is in between. All right, now how do we determine that? Okay, on the outer casing, a lot of times you'll extend it and you'll have a cap over here, and then here's your turn down. Now, what I can do, I can use a measuring tape that has a float on it. And I can run that measuring tape down through the well until the cork hits the top of the water. And then I can literally measure off of the end of my breather. That tells me the static level. Then I turn that pump on. Then I can lower that measuring tape all the way down till it hits the water again. And then I can remeasure. And I can determine what? Yeah, I can determine the pumping level, and then I can subtract the 2 and get my drawdown. Another method is using a electrical sounder. You have a wire that's hooked to batteries. And on the surface, you're going to have a light and an alarm. Now, it's got 2 prongs on it. And when you lower down into the water, when water will conduct electricity, when the prongs hit it, it completes the circuit, and the light will come on and the little horn will blow. Electric sounder. Then I turn the well on. Okay, drops down, then I can lower it down. As soon as it touches the water, it will send me a signal that I have done that, and I can determine my pumping level. Okay, it is the most accurate of all the methods. The one that can be on a groundwater test, though, is using a bubbler. And I always do this because every exam that I've ever seen in every state has this on there. So if you ever take a groundwater test, you need to learn how to use a bubbler. How many of y'all use bubblers? Anybody use bubblers?
It's the air pump, right? Airline.
Yeah, airline. Yes, sir. Okay, now, what I'm going to do is I'm going to run an airline, let's say over here, down the side of this pipe. Let me go on the outside, all the way down to a known point. Okay, now let's just say this airline is 300 feet down. Okay, now on the end of this airline, I'm going to have a valve and I'm going to have an air compressor. Okay, now what I do when the well is not running, I turn on the pump and I'm going to let it purge all of the water out of that line. Okay? And I got a gauge. Let me put my gauge on here. I got a gauge on here. And I turn off the air compressor, I close that valve. The water is going to compress that air and it rises up. And let's say on my gauge it reads 90 psi. Okay? Now, I turn my pump on. Okay? I purge this line again. Then I close the valve. The water's going to rise up until it gets to the pumping level. And let's say that it reads 60 psi on my gauge right there. Okay. Now I can determine the drawdown from this piece of information and the static and the pumping level from this information. Now, how do I know what is 1 psi? Let's look at it. All right. 1 psi. How do we determine that? Well, if you look at the Earth's surface, pushing down on the Earth's surface is 14.7 psi. That is known as 1 atmosphere. 1 atmosphere. So like when y'all recently got a hurricane that came in and did some damage. And let's say here's the ocean out here, and I get a low pressure zone out here or a vacuum. And I've got this thing spinning around out here. And let's just say that the PSI in the eye of the hurricane is 9 PSI, this vacuum. Well, on the outside, pushing down on the outside of this water is 14.7. So it's going to make the water rise up into the eye of the hurricane. And as that sucker moves to shore, this big wall of water comes on to shore and it wipes out the Galvestonites. That's the last hurricane we had. The Galvestonites got wiped out. Okay. And I guess up here it was the New Jersey Knights got hit real hard. Okay. So it comes ashore and it does tremendous amount of damage. Well, the same thing is in a pump. Okay, now, we know that water weighs 8.34 pounds per gallon. We know if you look at this box right here, if this was 1 cubic foot of box, 1 foot by 1 foot by 1 foot, 1 foot this way, 1 foot across, and then 1 foot lengthwise. So if you're looking at it like this, 1 foot by 1 foot, 1 foot in height. So if you took and you multiplied, and we know that that's 1 cubic foot, holds 7.48 gallons of water like you learned yesterday. Okay, that comes up to approximately 62.4 pounds per cubic foot. So that box of water weighs 62.4 pounds. Now, if I was to do this in inches, so if I did this box in inches, so this would be 1 square inch. So 12 times 12 is what? Remember yesterday, 144 square inches. But then I want to know what this 1 inch column of water weighs. So I got 1 square inch, that's 12 inches in height. Okay? So if I took 62.4 and I divide this by 144 square inches equals approximately 0.433, that's ugly 3 pounds per square inch, or 0.433 psi. Okay? Now, that's what water weighs per foot. So if I want to know with how many feet of water equals 1 psi, all I have to do is take 1 psi, divide it by 0.433 psi per foot. Of course, Miss Bessie showed you that yesterday. That crosses out, comes out to approximately 2.31 foot equals 1 psi. So, if I had another box and 1/3 of a box up here, and it was 1 square inch, and it's 2.31 feet high, weighs 1 pound on that little scale down here. Okay? Now, pushing down on the Earth's atmosphere is 14.7 psi. So if you take 14.7, multiply it by 2.31 feet per psi, this is psi, and this crosses out, equals approximately 34 foot of water, equals 1 atmosphere. Okay, so 34 foot of water equals 1 atmosphere. Make sense? So now, this is psi. Now, we know that the length of my tube is 300 feet. So, if I take my calculator, and if somebody takes their calculator and multiplies this out for me, I appreciate it. Take 90 times 2.31, this is psi, feet per psi. Let me put psi over here. So this is going to what? Cross out? Okay? And if somebody multiplied that, what does that come up to? Anybody have a 270.9? I'm sorry? 207.9. Okay, so if I take that and I subtract it from 300 feet, that comes up to what? That'd be dos, and yeah, and that'd be 9. What, is that right? Yeah. 92. So if I look at it, my static level would be what? 92.2 feet below the center line of that gauge. Okay, now let's do the next one, the pumping level. 60 psi times 2.31 feet per psi. And what does that equal to?
138.6.
138.6 from 300. That'd be 4. That'd be 1. And that'd be 61. That'd be 161. Is that right? So my pumping level would be 161.4 feet. I can take the 161.4 minus the 92.2. That'd be dos, 9. And that'd be what, 15. That'd be 69.2 feet. That would be my drawdown. Okay?
Or you can buy a direct read gauge.
See?
Or you can buy a direct read gauge.
That's even better. But on your test, I guarantee you, if you take the groundwater test, that possibly would be on there. Does that make sense? So far? Okay. Just remember this. We need to know the length of the what? The tube. We have to have a good gauge and a compressor and the valve to turn the compressor off. Isolate the compressor. And then we can determine PSI for both the static and the pumping level and get our drawdown from there. The other thing I can do, instead of doing all that, is subtract the 60 from the 90, 30 PSI, right? So 30 PSI times 2.31 would also give me nearly the same answer. Might be a little different, but close enough for government work. Mm-hmm. Okay. Any questions there? And hopefully that was helpful. All righty, so let me put my book back up here. It's like like this gentleman, he's got a straw in his drink. When he puts that straw in his mouth and he gets a complete seal and he sucks in on that straw, he's creating a vacuum. The pressure in his mouth is now lower than the atmospheric pressure. And so it's actually the atmosphere on the outside that's pushing down on the surface of whatever he has in there, scotch, whiskey, rum, whatever, and it pushes it up through the straw. Now, what makes it easier is the size of the straw. The what? Yeah, because of friction. And the viscosity of the material that he's sucking through. So as water gets colder, the more viscous it gets, the more difficult it is to lift because the molecules are closer together. But during the summertime, it is going to be less viscous, and so it's easier to lift the water. But most groundwater temperature is what? Very stable, yeah, very stable, though it doesn't fluctuate much. And so we go from there. You want to add anything to that, Ms.?
Sounds good.
All righty.
Did you say earlier, yesterday, I don't need to jump back, but did you say the water was very hot where you live?
Well, at College Station, Bryan, very hot. It's over 140 degrees,
And that's being,
pumped out of the ground.
so how, at what point would that cool off?
Well, what we do, we bring it to the surface and we run it through cooling towers.
Can you get deep enough to where you can get colder water?
No, sir. It's the water passes through such compression, the friction just generates tremendous amount of heat. Yeah, that water is passing, it's the real narrow aquifer. And it starts off real wide up country. Most of the water in Bryan College Station is coming out of the Fort Worth, Dallas area. That's where the outfall is. And by the time it squishes down into that little narrow band, it's under extreme pressure and being compressed, and so the temperature gets quite hot. Like I said, during the summertime, you still have to cool it just so you can take a shower. It gets that hot. You can't take a shower. I mean, it'll burn you. I'm sorry. I'm so hard of hearing.
It doesn't find a release point. Is it geyser up?
No, because it's very it's granite. It's almost granite type material. Yeah. When they drill down through that aquifer, they have to use diamond bits because it's that hard.
So when you done, when they pump, when they come through and have a well, it must shoot right up then, no?
It rises up almost to the surface. Yes, sir. Sure does. It's almost artesian, but it's not quite.
It's under that much pressure that's coming.
Oh yeah.
Pretty quick.
Yeah, it rises up almost to the surface, but it's really due to the compression between the two impermeable layers that gets it so hot. And it's very high in fluoride, but it does not pass through lime, and it's very soft water. When you take a shower up there, you can ask Miss Bessie, you think you're dirty because your skin has never been so clean. And it even takes out, I mean, it's only like 1 to 2 grains of hardness, and it's like 8 milligrams per liter of calcium carbonate hardness. It's something else. And so you go from there. All right, any questions so far? What did I do with that punch button? Oh, there it is. All right. So drilled wells is the most common. I'm getting a lot of light. Let me see which one. I think it's this one. I need to turn it up a little bit. Go the other direction. That better? Okay. As you can see, we have the cement stabilized material. We have the casing, and then we have our screen. And this is the gravel pack. And again, it must be what? Disinfected before it's put in, 50 milligram per liter dosage. And just remember, the diameter of the gravel pack should be only twice as big as the media itself. Twice the media itself. Because if it's any smaller, the grains can pass through the angular spot and get into your screen. Okay? That way you can lose larger slots. And vice versa. And the screen is, of course, to keep the sand out, not the birds or the insects and stuff like that. Okay, and we go there. Casing, we talk about the casing, well screen, and then the gravel pack, and then the vent. They really don't show the vent on here, but it's, you know, on the outer casing at the top, and it comes out so that you can prevent damage to the outer casing. And then well sanitation and stuff like that. Sealed, abandoned wells. This is a big problem in most states. A lot of people have maybe a little house well or something they have, and they don't properly seal them, and that is the #1 location for contaminants getting in well. I have been with an investigator one time up around San Antonio, and a gentleman had an old house with a well in there. And inside of that well house, he was storing some very toxic agricultural chemicals. And some of the chemicals had leached out of the drums and gotten into that well. And of course, that's not very good, is it? And so we have to be very knowledgeable of contaminants getting into these groundwater sources from literally, I would call them just plain flat illegal dumping is what I call it, and stuff like that. So protect with fences or locked well gates. And in Texas now and throughout the country, and the EPA requires in the Safe Drinking Water Act that all gates will be locked at all times. If you leave that gate open and leave and you come back, you have to call the United States Coast Guard, because it's going to be treated as if that water had been contaminated. So don't ever leave your gates open. Keep them closed, okay?
Cover gates around well houses.
Around the well houses and the wells and everything, yeah. They're very strict about that. And sealing block, meter, vent, sampling faucet, all of those things are necessary on the discharge side of the pump. Test bacteriological quality. It varies. Again, this is one of the things most people follow AWWA. And basically what happens, you have to collect 3 samples on 3 days, and all 3 samples must come back negative before you can put that well into production, okay? And again, you have to sanitize it, and you use 50 milligrams per liter of chlorine, and then it has to be in the well at least 6 hours, okay? Now, one of the things that we have to do is check this well. When the driller drills a well, and let's say that you want a well that produces 1,000 gallons per minute. Well, he's going to put the driller's pump on there. The driller's pump is going to test that well for production. You want that test production well to put out at least 25%, maybe even 50% more than your designed production. Now, he's going to put that in there, and he's going to pump it for a minimum of 30 hours. Now, you can shorten it for large wells, but you have to get permission from your state agency or from the EPA to do that, because some large wells, who wants to waste that kind of well? If it does not break suction, then that means that well will do what? Produce the necessary water that you're trying to achieve. So if I'm talking about 1,000 gallons, I would like to see him put out at least 1,250 gallons per minute for a reasonable amount of time, normally 30 hours. I said 30 hours, 36 hours. And then I know that well, okay? Will not. So we take the back T samples. We must pass 3 back T samples before I can put that system back in. Secure sanitary control easement. Sanitary control easement is a 150-foot radius around the well. And sometimes people live within that 150-foot radius. And so you have to acquire a sanitary control easement agreement with those people to limit what they do on their property. And then it must be registered at the local courthouse for it to be in effect. Now, a lot of times, the landowner will not give you that. Now, you can take them to court, but the only way you can get by without getting a sanitary control easement is by additional monitoring of that well at all times, probably daily or weekly at least. Does that make sense? So you can run more tests, but that gets more expensive for you, doesn't it?
Now, what happens if the well was in existence before they build that crop?
They don't care. There is no grandfather clause on that. Yeah.
I'm just saying, if they're infringing on that easement, on that boundary, aren't they legally obliged to keep the bill develop their property the appropriate distance from that existing wellhead?
No, that's just when it comes to sewer apparatuses and stuff like that. But look, that's a big area. You know, that's, land is so valuable. Now the city, most of the time cities look at where they can buy that area. You know, they'll find some place out in the country where they can buy it. But in the old days, land was considered very valuable. And so if you took 150 foot radius and you got this little old well over here, you know, might even be a house, several houses in that area. And you might actually only own a little small section of that area. You know, that's almost an acre, 150 feet, real close to a whole acre. And some homes are built on postage stamps now, you know, little bitty lots. So you have to acquire agreements with all these folks, okay? Make sense? Okay. And it must be recorded at the courthouse. Just remember this, if you cannot get one, then you'll have to get a variance from your state agencies, and you're going to have to do probably additional monitoring to make sure that that well's not contaminated. Anything else on that, Miss Bessie, that you know? Okay. And so we go from there. All right. And we've already talked about this, the sealing block, the breather on the outer casing. This is not turned down like it's supposed to, but this can also be used for testing the static level and also the pumping level. As you can see, we have the air relief valve. Well, they have two on this one. This one is I have no idea what this is. But this is supposed to have a vent. They have an additional one over here going to the inside with an air vent and a test. So I guess they're testing the water from the inside on this particular well.
One of the races drop an M-scope, you know?
Yep. Do that too. Right, and then here's the air relief, and then we have the check valve. They have the test faucet here and then the meter. I prefer to put the test faucet on the opposite side of the meter because the meter, sometimes when you're collecting samples, can interfere with your sampling. And then you have your meter, and then you have to have they don't show it on here, you have to have an isolation valve on there to be able to isolate it. And then they have the air vent coming from the outside. This has a lot of additional stuff on there. Yeah. And then they show the pressure cement, surface casing, and all those good things. And they show the pressure cement going on both sides. So this is a pretty good drawing right here. Really helps out. And all the vents need to be designed so that you do not create an overpressurization or a vacuum type effect on the system that could cause damage. Otherwise, we could get contaminants down into the well. Now, when it comes to safe distances, you got this 50-foot area. That is recommended that nothing be constructed within 50 feet of that well. Is that always possible? No. But if you get a variance, like if you have a line cutting across here, you would have to cement stabilize it, put in encasing, and it has to use pressurized pipes and stuff like that. There is cases where you have to do that. But if you're building or constructing a new well, try to construct it in an area that does meet that 50-foot minimum, okay? Now, outside of the 50-foot, you can have septic tanks, tile, or concrete sewers, okay? Outside of 50 foot, okay? Also, livestock and storm sewers, okay? As long as it's not a feedlot, say you have a pasture, you have a few cows out there, chickens, and cabritos, goats and stuff like that, more power to you. And then we have outside of 150 foot, septic tank, septic drainage fields, underground fuel storage tanks, and those must be outside of 150. Okay, outside of 300 feet, we have wastewater wet wells, like lift stations, pump stations. We have wastewater pumping stations and wastewater drainage fields. I'll ask you a question. This is on the water test. What's the difference between a pump station and a lift station? Well, a pump station is a force main. A lift station is when the lines get so deep, they lift it and they dump it back into a gravity line. Make sense? And that's on the water exam. I don't know why, but it is on a lot of state tests. And so you can have wastewater wet wells, wastewater pumping stations, and wastewater drainage fields. And then outside of 500 feet, animal feedlots. You notice over here you can have livestock, but when it comes to feedlots, they can be no closer than 500 feet. Wastewater treatment plants, solid waste disposal sites, and irrigation with wastewater effluent, which is becoming real popular throughout the country. What color is that pipe? Test question. It's purple. Not maroon, but purple. Okay? I wear maroon. But it's purpley pipe. And so it's used for irrigation of golf courses. And some people are, like in El Paso where I live, they're using it for processed water for manufacturing because water is so precious out there. Instead of they used to pump it back down in the ground, back into the Waco or the Mesilla formation. But what was happening, Mexico was pumping it out as fast as they were pumping it in. So they didn't want to give any more water to Mexico. So they're now, if you go out to El Paso, you'll see 2 elevated storage tanks, one with a big purple band around it. Well, that's processed water for manufacturing. And do y'all use any of y'all's wastewater here for processed water or anything? Anybody do that? Yep.
They do in Cranston, they use a little bit, I know, for that cogeneration plant.
Oh, yes,
They
perfect.
use it for cooling.
Yes, sir.
It's a small amount.
So they have a cogen over there, huh?
It's over actually with the Johnston landfill area, but they'll use some of the water just to cool the turbines.
Oh, man, that's great. Yeah, anytime you can reuse. Yeah, just a small part. Yeah. 10 4.
Over in Jamestown, there's a waste treatment plant that gets pumped over to a golf course.
Yes, sir. Wonderful. 10-4. It's becoming quite popular throughout the country. You take like some states, when it leaves the wastewater plant and it goes into the receiving stream, it becomes the state's property after that. So why give it to the state when you can use it for yourself, you know? So you have to look at it from 2 different. See, in Texas, we have 2 different types of water rights. We have riparian, which is groundwater. If the water is under you, you own it. But in surface water, all surface water is owned by the state. And the state gives out permits for you to use the river water or any of the waters that are surface. And the reason was Texas had a lot of Indian treaties, and the Indians controlled most of the water, and that's how they kept the peace. You know, they didn't want people to hoard the water, dam it up, and prevent other people from having use. So when they came to the agreement with the Indian tribes down there, they came up with the state owning the water, and you have prior appropriations for that. You get permits from the state to be able to use that water and go from there. All right, disinfecting the wells. Disinfect before use, and if you look over here on page, let's see, page 14-10, disinfecting the wells. Look down below the sand pumping. You'll notice that after developing and testing, a well must be disinfected with a chlorine dosage of at least 50 milligrams per liter. 6 hours or more. I'm a firm believer leaving it in overnight, at least 24 hours before I ever collect back T samples. Then I need to pump that well, clean it out, and then I'm going to take 3 back T tests on 3 days. Okay, so I'm gonna do one, say Monday, Tuesday, and then one on Wednesday. And all 3 must come back, what? Negative before I can put that well in service. Just remember, if you're using a gravel pack, you must disinfect the gravel pack with at least 50 milligrams per liter of chlorine before you place it in the well. All right? And so that's very important. 50 milligrams per liter, 6+ hours or more. Take back T samples. 3 samples show no coliform organisms. And then, after 36 hours of running, we're going to run both the physical, chemical analyses on the water. And on surface water, we do this once a year. But primarily on groundwater that is not under the influence of surface water, then we do this every 3 years. Every 3 years.
Company that does well redevelopments and whatnot, and I never knew the answer until I asked the guy. I says, how do you know how much to chlorinate your well? 50. He says, well, you got to determine how much water is in the column. That's what you're chlorinating.
Yes.
If you over chlorinate, he said it can kill you because it will work its way out, stop killing bacteria outside, in the aquifer, and it creates food for more bacteria. So now you're creating a bacterial issue.
Here's the thing about disinfection. When you drill a well, there is nothing there. But when you disinfect a well, you're only disinfecting the things that you're installing in the well. Believe it or not, the contaminants are restricted to that column. It cannot migrate. Because the filter the media acts like a filter, and it will not go more than 1 inch. It'll stop it dead in its tracks. And it's really amazing how that works. But when you talk about disinfecting, we'll use some of the things that Miss Bessie taught you yesterday in math. Okay? So if I already know the static level, and I know the pumping level, and I know how far my well is drilled. And so we know that, let's say I have a 12-inch screen, and let's say that screen is 300 foot in length, just hypothetically. Then we know that the formula she gave you yesterday, pi r squared times the length of the screen times the 7.48 gallons per cubic foot equals gallons. She gave you that, okay? Then let's just say I have an outer casing and I have 200 foot of water in here, and let's say this is 18 inch, okay? And I've got 200 foot because I ran the static level, didn't I? Okay? I know the length of the pipe, so I can figure that bottom out. I can use that same formula, add the two together, and get the total volume of water. Okay? The total volume of water. And let's just say I worked it out and it came up to 10,000 gallons of water, hypothetically. Then you knew the formula that she gave you for dosing. And let's say that I'm going to be using HTH, 65% HTH. And she gave you the following: million gallons times the 8.34 pounds per gallon times the strength equals pounds. And we want to divide that by what? The percent strength of active ingredient, okay? And that would give us the total pounds of 65%, okay? Now, here's the thing. If you use 12% bleach, there's 1 pound of chlorine in every gallon of 12% bleach. Okay? So in 6% bleach, there's 0.5 pounds of chlorine. So if I come up over here, let's say I came up with 4 pounds. How many gallons of 12% bleach would I need? If there's 1 pound, 4 gallons. Now, if I'm using 6%, say I go down to the grocery Wally Mart and I buy 6%. How many pounds is in there? Half a pound? So how many gallons would I need? 8 gallons. Sto bueno? Poco bueno? I've got to stop there. Does that make sense? Okay. All right. So it'd be 8 gallons or 4 gallons because there's 1 pound in 12%. 12.5% bleach, which is more common, has about 1.06 pounds. So give them a little extra dose. To heck with it, you know. Don't worry about it. And goes from there. And that, you know, the Chlorine Institute is the one who came up with these numbers of 12 and 6%. The reason is they wanted to save you on math. The 5.25% bleach was a little bit less than a pound. So that's why they asked the industries to come up with the 6. Now HEB and Walmart and Target have come up with 8% bleach. Have you seen that one, Miss Bessie?
I have not.
They're in the stores now.
Really?
Yes.
Now, I do have a question though. If we want to go to Walmart, HEB and use that bleach, does it still have to have that NSF?
You don't have to have the NSF. A lot of them don't have that, but you have to call your government agency to see if that bleach is approved. Used to, they published a list of approved bleaches, but unfortunately, the industry didn't want to have to do all that government paperwork. So now you have to call the state to see if that bleach is approved. Now, Hill Fair back in Texas, Walmart brand are all approved, but you still have to call. But it is written on the MSDS sheet. So if you get the MSDS sheet, it might not be on the container, but it is on the material safety data sheet or data sheet.
Should be able to print that.
Hmm?
Should be able to print that off the computer.
Yes. Yes.
It's trying to get an answer from the state.
Yeah.
That's the one that's gonna have, you got, well, we'll be out of service for 6 months till they even open the envelope.
One office, they say it's all right, and another office won't.
But here's something that I always suggest is it's expensive to buy bleach at Walmart and your different stores, Target. If you go to your commercial supplier, like if you go down and buy a gallon of 6% bleach at Walmart, it normally runs around $2 and something. But if you buy it from your commercial dealers that is NSF stamped, they run around $1 a gallon.
You get from any pool supply.
Yeah, pool suppliers, they handle it. Yes, pool suppliers, they handle that commercial bleach. Yes, they do. And so that's pretty good. Just make sure it's approved though, okay? That's the most critical point. That's a good statement, Ms. Bessie, because I know that the state of Texas used to have an approved list, but it was so much red tape for the industries, they quit doing it. Yeah. So look at it. And then some of the terminologies again we'll review. We talked about what we known as the static level, and then the pumping level, and then we talked about what was known as drawdown in your test. They called it a drop down, but that's made it wrong, you know. And then we talked about the different components, and I like this. We have our motor. The main thing about a motor, let me tell you something. More people when you wire your electrical motor, remember it might not be turning in the right direction. So before you ever hook the motor to your shaft, make sure you check the rotation. I had several people that hooked it up, thought it was right. They color coded everything, sent the motor to the motor company to get it repaired. They rewired it backwards and they turned it on and unscrewed all the bolts off the bottom. And then they had to go and fish it all out. And that has happened several times. So,
Some of them are ratchet protected.
yes, they have the ratchets on there. That's good.
So they lock up and then they open
Yeah.
against the heaters and that just break it trips.
Right. And those are good. The ratchet on there. And right on the top of the motor is a ratchet. That nut up on the top, when you tighten it to the shaft, there's a ratchet there, and that works really good. You can see your discharge, and you can see all the different bearings holding it up. Then you get down to your bowls, and then you have your suction screen and all this, okay? Now, the next thing I want to talk about, though, is the bowls themselves. Okay. Now, let's say that I need a well that produces 1,000 gallons per minute. 1,000 gallons per minute. All right, now, and I've got to go, my total discharge head would be 400 feet, okay? But let's say I have a bowl that puts out 1,000 gallons per minute, 100 foot of head, max. So, how many bowls would I need? Need 4 bowls. Does that alter the GPM? No. Okay. So when you hook up bowls in a series, so I'm going to have a bowl, a pump, and a pump. And here's my suction down here. And I've got my, okay. Now, I've got all this water up here pushing down weight, okay? So this is positive head, okay? Positive head. Now, what happens, that's going to be pushing up into the eye of this first impeller, okay? Now, what happens, I'm going to increase the head each time. It's putting out 1,000 gallons, but each time it's got vanes. This is what we call a vane pump. And it forces the water up into the eye of the next pump. And thusly now I'm at 100 foot ahead, let's say. And when I get to the second pump, I'm at 200 foot, 300 foot, and 400 foot. Okay? And thusly I'm overcoming the head pressure, the weight of the water. But did I change the volume? Now, let's just say that I've got 1,000 gallons here and 1,000 gallon pump here and 1,000 gallon, but the pump manufacturer actually ended up messing up and he put a 750 GPM bowl on there. What is the maximum amount of water I'm going to get out of that sucker?
So it's
750.
the least amount.
The bottom pump depicts the amount of water, or the bottom bowl. So it's very important that you make sure you have the right system put together. Because if they make a mistake, and that does happen, it's happened. They put the wrong bowls in there and hook it up. Now, let's talk about hooking up in parallel. Let's say that I have 3 wells. Okay? And I have 3 wells, and I have them coming up. And here's a well, and it comes up into a header. Okay, here's my header, and I got another well coming in. Here's a well, and another well coming in. Let's say each one of them puts out 1,000 gallons per minute coming into my system, and this is going over here to a ground storage tank. Okay? Now, each one of these is designed to go, let's say, 275 foot ahead, 275 foot ahead, 275 foot ahead. All 3. That's my head. But pump number 1 is running. How many gallons per minute am I getting? I'm getting 1,000 gallons per minute at 275 foot ahead. Now, when I turn on pump number 2, at the same time number 1 is running, what happens to my head?
Well, the head goes way up and your output drops.
In reality, it goes up slightly, but it's not going to increase head. Theoretically, it does go up a little bit. But what happens to my GPM?
Just double. Just double.
It should theoretically, but does it? No. It depends on the size of the header. So let's say I have a 6-inch discharge, a 6-inch discharge, and a 6-inch discharge. Then my header needs to be sized so that I can reduce that friction enough that I can achieve the highest GPN I can. But if I was going into, say, a 6-inch header, velocity is going to increase. When velocity increases, what happens to friction? Increases, reducing flow. Yeah. So I have to consider the size of that header when I'm tying maybe 3 or 4 wells together. Make sense? All right. Very good. Okay. And submersible wells. Submersible well is where the pump, I'm sorry. Right. And of course, submersible, the pump and the motor both are located in the water. And I like this. The reason is you have less friction, plus the water helps to cool the motor, and you don't have a shaft to worry about and all this other. The only bad thing is to work on the motor, you have to take the entire well out. And plus, you need to worry about electrical lightning storms and stuff there. So it needs to be protected from lightning. That can be a serious problem. And then vertical turbine is where the motor normally is at the top. You got a long shaft with bearings going down to the bowls itself where the pumps are located. And then we have series. We talked about that. Each bowl is designed to overcome head, but it does not increase the gallons per minute. And groundwater treatment, aeration. You know, air is a natural oxidizer. It can purge gases like hydrogen sulfide, methane. It also helps with iron and manganese and things like that. It helps to relieve taste and odor problems. And so aeration is very, very good, very economical. A lot of times when you pump out of the ground, if you're having these things, they'll use like a cascade system, or they'll pump it through a tower.
I got both.
Do you? Yeah. And that really helps. And then like up at College Station, we use it to help cool the water also. Yeah.
It reduced my, because I use calcium hydrated lime for pH adjustment.
Oh, do you?
Yeah, and I was able to go from, because I'm going back 20 years before we did it, we pumped, when the well went right through a treatment facility, we were using upwards of 500 pounds to treat 1.5 million gallons.
Mm-hmm.
I went down to 70 pounds,
Wow. Yeah.
just from aeration.
Just from aeration.
Yeah.
Wow. Yeah, that's pretty good. Where I live, we have sulfur problems. We have iron. We have a little bit of junk, all kind of junk in there, you know, most of that water. And of course, when you get used to it, you don't think about it. But when people come to visit you, they drink bottled water. All right, corrosion control. Remember, when the water comes out of the ground, especially groundwater, normally the pH is going to be higher than 7. But in some parts of Texas where they have a lot of acidic growth, some of that stuff that is percolated down there is a little bit more acidic, and the lower pHs. Because like where I live, Texas is a lime infested state. It's got a lot of limestone. And so most of our water is fairly hard, and so we don't have to worry about it too much. But we want the water to always be stable. And of course, in your book over here, we talk about corrosion control. If you look over here on page 1413, you can see where some of the adjustments, aeration and pH adjustments with sodium hydroxide, soda ash reduces corrosion. So those are a couple of good answers. Sodium hydroxide, soda ash will help with corrosion. Softening, where I live, like I said, we have very hard water, is anywhere from 400 milligrams per liter up to 600-700 milligrams per liter of hardness. And that is as calcium carbonate. That's not permanent hardness, okay? And so we usually use water softeners, sodium chloride to help reduce the hardness of the water. We also use ion exchangers to help reduce the calcium carbonate in the water, and that works quite well. The biggest one that is used throughout the country still is where we're using sodium chloride to help reduce the calcium. Sodium has a stronger attraction to the carbonate than calcium, so it knocks the calcium off, and thus the sodium replaces the calcium ion, reducing the hardness, okay? And then a couple other things is special processes. Oh, how do you say? A few years ago, well, actually almost 30 years ago, the dentistry organizations pushed for adding fluoride to water. Do y'all add fluoride to y'all's water here? Yeah, and you know, dentists were in the business of trying to protect, you know, children's teeth and also adults' teeth. So they started adding fluoride to the water. Like in College Station and Bryan, that is an exception to the rule because our water is high in fluoride in College Station. And so we use materials to help reduce the fluoride. And of course, it is both a secondary and a primary contaminant. In primary, it cannot be above 4.0 milligrams per liter. In secondary, it cannot be above 2.0 milligrams per liter. And of course, what's recommended is about 0.7 to 1 milligram per liter of fluoride. And of course, the most common one used is fluoric acid. What else is used, Miss Bessie? Yeah, and right, there's several that are out there that they add. But they've noticed now that children's teeth are starting to get modeling, you know, the staining of the teeth, because everything that we have now has fluoride in it. Toothpaste, water, even other stuff, they add fluoride to it. So children's teeth are now starting to get the modeling effect. So they might reconsider that. I don't know.
There's also a study now with fluoride that they did some studies with children in China who are not exposed to it at all, and found out that fluoride actually decreases the IQ of children.
Reduces the IQ? I was wondering what my thing was.
So they've actually asked that, I think it was the EPA, as a matter of fact, maybe 2-3 years ago, came out with a statement that, you know, we need to have the public water supplies the lowering of fluoride in the public water. So.
Yeah.
Ours was lower, because it used to be, like you said, 0.8 to 1.
Mm-hmm.
Now we're under 0.4 to 0.7.
0.4 to 0.7.
Yeah.
Oh, one.
In that range.
10-4.
When I read a study about that because everybody's drinking bottled water, you know, and they don't have any, like homes, you don't have to follow anything there, and there's not a lot of fluoride in those waters, that tooth decay in children is worse now, because they're not drinking water that has, they're getting well water, because it's well water that they're drinking, supposedly in bottled water.
Yeah.
There's no fluoride in it. So I guess it's good and bad for both sides. There's compared to like before you start drinking a lot of bottled water, the children of that age, like my age,
Yeah.
The tooth decay nowadays is worse. I took a study. That's just something I read in the magazine.
Yeah. And most bottled water now is run through RO, and it's been demineralized, and
Nothing in it.
and unless you add minerals back to it, actually it can cause health problems too, because your body needs minerals, and water will seek equilibrium, so it can actually demineralize the body. So a lot of companies now are adding a little bit of electrolyte with it to help stabilize the minerals in it and stuff like that.
Now that they call it vitamin water. So
Yeah.
They basically took it all out, put it back in, and
Yes, sir.
Rename it.
like my father said, my grandfather knew what we paid for water out of bottles and probably had bottles.
Yeah.
People like it. So.
10-4. Of Coagulation and sedimentation, you know, it's not used much for groundwater, but in some parts of the country where they have influence of surface water, conventional treatment is being done. But I'm going to tell you something, folks. If I was to build a new water plant today, with all of the chemicals that are popping up in our systems, I would go with RO. RO has gotten to be more economical, plus all of the pesticides that are in water. Pesticide is anything. It could be an insecticide, herbicide, nemicide, fungicide, algicide, anything. But because of the heavy chemical uses in the past by farming and everything else, and it has become a major concern. Pharmaceuticals, you wouldn't believe. You know why the fish are a little stiff nowadays? Viagra. I hate to say that, no. But it is true. We ran a test on some river water. We ran the ECLOX for Homeland Security. And the barbiturates and the hormones in water is over 5 parts per million. Now, that means there's a lot of, how do you say, chemicals going into the water just from pharmaceuticals. And then you wonder why people act the way they do. It's in the water. No. Okay. So, and then reverse osmosis. I really like reverse osmosis in the future because it's one of the few methods of treatment that virtually removes everything. And let me tell you something, they're very simple to operate. Personally, I've never operated one, but I work out at El Paso, and I work over there at the Lee Trevino water plant, and it's an 80 million gallon per day RO plant. And the operators over there that I worked with tell me it is simple compared to conventional treatment. All you're doing is watching pressures. You make sure the membranes are cleaned. Pre-treatment is adequate, and they say it's very nice to operate. They don't have to work very hard anymore. And main thing they do is watch pressure and clean the filters. And yeah. Oh, did you?
And we had a fireman that didn't watch the pressure, because basically if the pressure isn't where it should be, it's just going right through the membranes.
Oh, broke through?
So basically the next morning they were drinking salt water coffee. I don't drink coffee, so it's funny for me to watch.
Yeah.
I was like, and we went over and the pressure on one side was basically 0. So if you're doing salt water, it's a little tougher than, or you better watch it a little closer.
Oh, yeah.
You gotta clean a little more.
10-4. Yeah, that could be.
Otherwise, yeah, you'll know your water.
The footprint on those things is really big, so you need a lot of room. But,
Yep.
especially if you're treating an appreciable amount of water.
Yes. The 80 million gallon per day plant in El Paso is probably about a half an acre in size, wouldn't you say?
Don't know about that one. I know we saw some in the Virgin Islands.
In the Virgin Islands, yes.
Where they
Yes.
were to using them for salt
Yeah.
water. And the area was really not that big, and they were doing about 130 million gallons a day.
Mhm. Yeah.
They got both, you know,
Yeah.
the ones that they have for yachts and boats are not.
Yeah.
They're not that big.
Ours was only, it was only like this big. Now, I went on a yacht that makes it, and he had one that was probably as big as this whole table.
Yeah.
2 big.
Oh, 2 big ones,
two
yeah.
Big ones, right?
Mhm.
So obviously it depends on what you want,
Right.
how much water you want to make. You can get them that only make 10 gallons a day if you wanted that, I guess.
So now you get, so just by reading it, it seems like you're generating quite a bit of hazardous waste too. Now
Well, let me out at
They've got them nowadays where,
Yeah.
again, in the old days where 50–60% was waste product.
Yeah.
Now they've gotten it down where you can produce where there's only 20–40%, even less.
yes.
So
Out at-
technology is improving.
Yeah, out at El Paso, they're taking the brine water, and because they're using brackish water from the Hueco Formation and the Mesilla, and it's actually improving the other aquifer. even though the concentrate is so strong, the other one is so high, it's actually lowering it. But they're using it to raise a special shrimp out there now, Camarones. These shrimp love this salt water. And it, you know, you and I we could walk on it, it's so thick. But, you know, it's almost like Salt Lake City, the Dead Sea, you know, so much salt in there. And, but they're finding other uses for that salt water. And so it's really, and then surface water influence, they're known as GUIs, groundwater under the influence. And most of the time, this impermeable material really is not impermeable. There's fissures, there's cracks, there's spider cracks in there, and eventually materials can get down into your system. You know, even clays eventually allow material to pass through and get into your aquifers. If you have limestone, it's got a lot of large cracks in it, fissures and stuff. And if you have a growth of people and a lot of wastewater collection system added to your system, lift stations, they can, you know, overflow now and then, and they're getting down into the aquifers. And so the way that we tell if it's a GUI is, you know, normally groundwater is very stable, temperature, pH, and also it's free of organics and no bacterial growth at all. But under the groundwater rule, which Miss Bessie's going to talk about this afternoon, we're going to look at each one of those elements and how that can indicate that our groundwater is under that influence, and thusly we have to take additional precautions, microfiltration, ultra, nano, or even reverse osmosis. And she'll get into that this afternoon.
I think it was 91, we tested 2 of our wells for that, MPA testing, microparticulate analysis.
Yes.
And what they did was over the course of 24 hours, we ran 1,000 gallons through basically what amounts to a whole house filter. Then that was sent out for analysis, and then they look at that to see what that filter trapped over that 24-hour period.
Right.
And believe it or not, I mean, I got one well that's sitting on a mound of land in the middle of a swamp, and that was not under any influence of surface water.
Yeah. That's what I was saying. Just the slope of the land can have a marked effect. I guess the biggest one was in Walkerton, Ontario, where the well was not cemented in properly, and it flooded, and they had just spread cow manure over there, and it got inundated, and 8 people died.
Like 400,000 people got sick around.
Yeah, yeah, and it was a bad thing. And of course, Walkerton, you know, I mean, that was something. But then Milwaukee, the one you're talking about, Milwaukee, where cryptosporidium got into the intake, and they don't know how, but the intake used to be right where the rivers all came together, and they figured it came from a feedlot upstream. But who knows, you know, it's just one of those things. And impact of shallow at-risk wells. Remember, anytime you have table wells, there is no impermeable material above it, so you have to do more extenuating testing to make sure that that water is safe to drink. Disinfection is very important. Up at Wichita Falls, they treat it as if it was surface water, and they have to have backup systems to make sure chlorination is going on, and they're checking for crypto and giardia quite extensively in those areas. So we go from there. And then the surface water treatment rule. And basically, if you look over here on page 1414, and when we talk about the surface water treatment rule, groundwater that is under the influence, and Miss Bessie's going to go over that this afternoon, the surface water rule, groundwater rule. And how do you say, like this gentleman was just saying, there's a lot of testing that has to be done to ensure that that water is safe, free of bacteria, viruses, and protozoan. Remember, chlorine does not kill cryptosporidium. And most of the times it doesn't affect giardia either, or anemic dysentery. All of those are protozoan. So we have to be very, very careful. And they're going to talk about how to evaluate surface water. We're going to talk about giardia, evaluation of influence. But if you look over here on page 1414, the last thing, how to evaluate surface water influence. Look at the second paragraph. Normally, this is normal now. If the well is deeper than 50 feet and more than 200 feet from a nearby surface water body, is constructed properly, that's the key, is screened or perforated below a confined bed, and has no water quality shifts, coliform contamination, or indicated disease outbreaks, extensive evaluation is not required. But those are a lot of elements to fulfill. You know, to be able to say that your water is not under the influence is up to you and I as operators and as well owners to prove that that well is safe. A long time ago, the government had to prove that the well was not safe. Now, the shoe is on the other foot. It's up to you and I to make sure the water is safe. Okay? So normally, if the well is deeper, the outer casing must be at least 50 feet below the surface, passes through an impermeable layer, be properly sealed using pressurized cement from the bottom of that casing all the way to the surface, proper installation of sealing block and everything else. Then you might be reducing your risk. But can you ever reduce the risk totally? No. So those are the things we have to look at. Any questions? Is it chow time? It's chow time.